think after lunch, probably hearing a theoretical subject is very difficult. But I will not give more on theory, I will just try to entertain you probably. Okay, the first talk is more on introduction, so that's why I went a little bit faster. But this is more on something like very important in the current scenario. For example, if you take, you want to duplicate the human with respect to robo, so definitely the robo is supposed to have mobility and as well as maneuverability. So both, if you are actually like providing, obviously you need to have some redundancy like our human arm. So if you take any human arm, so minimum degrees of freedom which is having is 7. If you are actually ignoring the finger degrees, so 7 degrees of freedom is there for human arm. So that redundancy is actually advantage. The same way, if you make any robo, that robo should be redundant. And similarly, if you are working with service robot, the robot should have over actuator. Why? Because sometimes actually like you may end up with some failure in your actuator. So definitely you need to have something which will overcome that or anticipate those parts. So the system should be kinematically redundant and as well as over actuator system. If you see any robo which is actually in service area, or you can say something like exploration, that robo will be having more degrees of freedom. For example, if you take the yellow robo which I mentioned here, this is obviously redundant. Even the mobility is actually like with the base probably 2, but the manipulator is having 7. So overall, if you take this, it has 9 degrees of freedom. It record only 6, but it is having 9. So similarly, if you take any robo which is in service, so obviously the system will be redundant. So first of all, I will just like split it into all the words and I will try to relate that. So first, we'll just talk about kinematically redundant. What is that meaning of kinematically redundant? So basically, it will be redundant in terms of kinematics. It is not in terms of dynamics. If you are actually taking the other side, over actuator system, which is redundant in terms of dynamics. For example, your dynamics. So if you are writing equation, generalized equation, mq double dot plus so pq dot plus gq equal to tau. That tau is actually like over actuated in the sense it will be having more. So it will be b into something like f. The f is actually more than 6. For example, you will take 6 degrees of freedom. That over actuated means basically more than 6. So this is actually in terms of dynamics. But if you say the redundancy in terms of position or velocity, which we are actually like kinematics only. So it is kinematically redundant. For example, I already told. So the manipulator which is having 7 degrees of freedom, which is kinematically redundant. It is not dynamically redundant. It is kinematically redundant. How it is kinematically redundant? The same question you can actually like reach in a number of possibilities. Very simple example. You just imagine there is one mobile robot. So this mobile robot is having 2 R manipulator on the basis. Now this horizontal question can be reached n number of ways. For example, I keep this on. Still the vehicle actually can go to and fro, correct? So you have multiple solutions possible. So this is what one of the critical thing. Okay. So how this will be beneficial? First of all, we have to think. So this will give. There are 2 things. So the task phase is actually fixed. For example, I want to fix this xy and this theta, but I have still 2 more degrees are free. So which I can actually like make a self motion. Very simple example with the same case I will take. So this is the path. Okay, this is supposed to be a desired path. Now there is a vehicle. So I am just ignoring this vehicle is supposed to follow this. So somehow there is an obstacle here. Still this path can be followed with this end effect. Even there is actually like obstacle here, still this will go like this. Still it will go through this. So which we call like a self motion which will be exist. So this self motion can be utilized in a number of ways. One of the easiest way for avoiding obstacle, but the other important aspect which is working on kinematically redundant system is energy optimization, or you can say resource optimization. Because these all the systems are going to deploy in a service environment. Service environment always like end up with the endurance. For example, if I deploy an aircraft in a space, so how long it will survive to take a survey and come down. So if I have more energy consumption, it may take only lesser, or you can say it will take less duration. If I have less power consumption, it may take longer duration. So the endurance will be higher. So people always try to minimize the energy, or you can say minimize the time, or minimize the resource. So this is what the major concern which is actually behind this kinematically redundant system. This can avoid obstacle, this can avoid limitations. For example, morning professor told, like Professor Gosal told, certain path in task space, probably like 30 plus or minus 30 is a restriction in one particular joint. But if it is a kinematically redundant system, one another joint will adjust so that it will be within 30, but still it will achieve that task. So that's what we are actually like thinking. So based on that only I mentioned, there are two tasks you can fix it. One is primary task, which is, for example, task is trajectory tracking. That is one of the tasks. The secondary task you can add, like you can actually like make force can be controlled, joint limit can be controlled, energy may be minimized. Like that you can actually like add with the help of self motion. So this is what one of the advantages. So this particular system, how we will actually like address, how we will actually like solve. Okay, this is what we are going to see. So one of the simplest example for over-actuated system, probably this is I taken a video. Okay, I'll show you that video probably. So this is actually like one of the underwater vehicle which has 4 thruster, but the thrusters are actually like rotatable. We call azimuth thruster. It is rotatable thruster. The thruster can be connected with, this is connected with the one servo motor. That servo motor actually like rotate this thruster. This thruster will give force in this direction, but now if we actually like move, so it will actually give multiple degrees. So indirectly it has 8 degrees of freedom in terms of controlling. It has 8 control inputs, but the required is actually 3. Similarly, you can see here, so there are 4 thrusters on top, 1 thruster in lateral, and 2 thrusters in the back. So it is not clear here. So totally 7 thrusters. This is also overactuated system. So if you are having a overactuated or probably like kinematically redundant system, what you can do? So this is what your generalized dynamic equation. But you know the generalized kinematic equation, which is we call, this is actually like you can say the joint space and this is the task space. I'll just write one of the simplest equations. So the same thing if I write, so x, y, b. So I call this actually theta 1. So this x task space, so this xt I can actually get with all the elements. So this is x plus, so L1, so cos phi, plus this is L2. So similarly I can write yt, similarly I can write theta t. Theta t is actually like theta 1, theta 2 and phi. This is actually instead of cos it will be sine. So now you can see that this is what your required task space in plane. If you assume this is a plane, so these are the 3 points which is actually involved in task space. This task space, if I actually like call this is for example mu. So if you recall your inverse kinematics or forward kinematics, whatever. The forward kinematics says that your joint space variable will be function of which is actually giving your task space variable, which is xt, yt and theta t. This is actually like function which is x, y, so phi, theta 1, theta. So you can see that you have 5 variables and you are trying to control 3 variables. So now if we are actually differentiate this, this is what we call generalized kinematic equation, which will give mu dot, so j into q dot. So this is what we call Jacobian matrix. If you remember in your kinematics course, so we call this the Jacobian matrix. So in this case, this Jacobian matrix will be like 3 into 5. In this case, this is a rectangular matrix, correct? So if you have a rectangular matrix, and that too like it is actually like over-actuated or probably kinematically redundant system, you have a freedom because this is known and you are trying to get this, or this is known and you are trying to get this. You have a link between this. Okay. right now what is our focus? Our focus is actually like trying to follow this. Indirectly we will be knowing this and this velocity and acceleration. So indirectly, like you have 3 is known and you are actually trying to find 5 unknowns with the help of Jacobian matrix. So now one of the easiest way we will actually like use the pseudo inverse. So if you recall pseudo inverse, the background, the Pan moves or pseudo inverse you can call. So the background says it is a least square basis. Indirectly, this will give minimum norm. So if I apply just j plus into q dot, so this is the least possible velocity of joint space. Okay. This way itself I can actually like minimize the total energy required because I got already minimum norm of velocity. So if I involve any process based on this, I can actually like go from. So based on this Jacobian, there are number of we call resolved. Okay, this is one of the resolved way. There are a number of resolved motion control schemes are available. That we will see one by one. So now this is what I mentioned here. You can see this way we will get. Only thing I have used the Q here. There is actually eta. That's all. So nothing else is actually changed there. So based on this, what we will actually like it. So for example, this is the system where like 4 thrusters and 3 manipulator motors are there. So totally 8 thrusters, 4 in horizontal, 4 in vertical and 3 motors. Similarly here 4 rotatable, so 8 control inputs. So these kind of cases, so I can apply the Jacobian matrix and I can actually like get the control input like this. So now this E is actually like my control input matrix and this is what your input. So the thruster TD is actually nothing but the thruster drive and this E is actually like my thruster configuration matrix. So in this case, let's see. So in this case or in this case if I see the thruster it will be like higher. So now I can actually like recall my entire dynamics in terms of simplified way. So now we got this. So now if I actually like bringing this, so I know this is what is generalized dynamic equation. I can substitute and Q dot I can substitute again based on this. Q dot is actually like J plus into. I can actually like get everything in terms of single space. So that space I can actually like use it. So this way I can make the system and then I can allocate whatever the control activity which is. So this is the way we can actually like simplify the system and then we can make it. So based on that, what we'll actually like get, one of the better advantages is energy. So it is energy efficient control. We use this kind of thing. Why? Because we are allowing the self motion in such a way that it will take less energy. Very simple example, you just take a bigger, you can say something like a roller, probably you can take a drum. Okay, you just take a drum, the drum lateral side you can see that more frontal area. But in the front side probably like lower frontal area. If you actually like put any of the drum in the moving water, automatically the drum will actually move and it will go like this. Did you notice that? So how it is happening? So nobody actually told him or told that you change this direction and go. So this is what we call self motion. So for example, you take underwater vehicle, especially inside water, there is actually underwater current passing on top of this. So now, if you are actually like taking a larger frontal area, the underwater current is sitting in the lateral side. So it is a large frontal area, more drag force. For example, you take bike and probably Activa. If you ride in a windy road, you can see that the Activa will not be stable because the wind direction is actually sideways because it is much of the things are covered. But if you are going in a cycle or probably bike, you may not get that kind of drag force. The same thing only. So now what we can do if you are actually like aligned by forcefully along the current. So what will happen, it is actually like attacking a smaller region. So the power required to overcome this less. So now there is a vehicle which is connected with a manipulator. You can actually move the vehicle the manipulator will do its own task. I'll show one video, then I will come back to the scenario. Okay. So you just imagine the first case is actually like trying to control the vehicle with fully actuated. Like all the states are trying to control, and the vehicle is supposed to follow the circle trajectory with the interceptor. This is actually like fully actuated, but it is actually compensating the current. This is not compensating, this is compensating the current. It is actually trying to follow. The other one is we are allowing the free motion with a pseudo inverse. So now the vehicle is actually like, initially it is jerky, but after that you can see that it is trying to follow because this vehicle is automatically aligned with the current. It's a 2D case, so it is automatically aligned with the current and it is trying to follow the profile satisfaction. Okay, in satisfied way. So this is what we are actually like trying to get out of this kinematically redundant system. Okay. So now the background I will actually explain here. So the background is actually very simple. So whatever I derive the equation based on that, the vehicle is having two thrusters and this have a two motor manipulator motor. So now I need to follow the x and y of the tip of the end effector. I am not bothering about the orientation, I am just bothering about the end effector point. That point need to be maintained, but my vehicle can go anywhere. This is what I was giving. The vehicle will not go automatically anywhere out. It will have some standard way, by forcefully it will follow that. Okay. So this is the equation which we derived here, the same thing which is elaborated here. And you can see the general solution of the forward kinematics I have given. So here there is one null space. So this null space only creating the self motion. So I will not tell much about null space here because that is big mathematical background is there with that. So you can actually like follow it. So now I have used very simple control law. So where I try to minimize or reduce the velocity of the system, but I am trying to reduce the position error of the task space. So I have used a simple PD but not straightforward PD. The derivative term I have used only for system velocity minimization, or you can say system velocity should be 0. But my task space question need to follow. So you can see this is actually proportional value, but it is proportional to task space. And this is a derivative word, but this is actually related to a system, which is we call the body. Okay. So now we call this a null space control. So based on this actually like we are actually like getting this. Whatever you have shown, like you have seen the video, the same video output as plotted here. You can see that the fully actuated is actually like following exactly the same way it is actually supposed to. Fully actuated with current compensation. But fully actuated without compensation, you can see that it is deviated because the current is not compensated. But the under actuated system, which is the blue line, it is actually using only two thruster and two motors. Still, it is actually like trying to follow. And what beauty thing is, if you look at the power. So we have conducted the same experiment in our towing tank. I will show you that video also. So based on that, you can see that the vehicle power is taken 1.1 kilowatts, but with the fully like current compensation, it is taking 5.8 kilowatts. And similarly, if you take the total power including manipulator and sensor, all those things, it is taking only less than 5 kilowatts, but that is actually taking almost 27. So this way we have actually like utilized the simple control law where actually we have minimized the total power consumption. So this is almost like 5 times reduction. So I can end up 5 times higher endurance with the same system I can deploy in underwater or probably outside. The same thing we try to like employ with 3D system, or you can say spatial system. So spatial system, the same thing will not work. Can anyone say why? Because it is in plane, it was working. The same case in the spatial, it was not working. Can anyone say what is the background behind that? Because here only 3 states we were thinking about, X, Y and heel, or you can say something like heading angle. But here actually it involved 2 other orientations. In that 2 of the orientations are very critical. So this spatial vehicle will have roll and as well as you have pitch. Since it is actually spatial, the gravity, buoyancy, all those things are involved. So even your buoyancy is actually little shift. Buoyancy and like center of buoyancy and center of gravity is even neutrally buoyant system, but it is actually slight shift. So there will be a pitch. If you have actually end up with a pitch, so obviously the system will actually like come down. You just imagine there is a pitch. It is actually upward or downward. Usually the end effector is in the front, so obviously the pitch will come in bottom way only. So it will be like this. So now imagine we are actually saying that the center of buoyancy and center of gravity is actually in the same plane. You just imagine that is opposite. Then what will happen? Even you are not putting anything, still roll angle also will be there. So these two are actually like the, you can say, culprits which was not helpful for the same scheme to implement here. So what we did, we actually like slightly modify the scheme. So we have used the same, which is what we have seen there. The task space proportional and you can say velocity for system velocity. But we have done one thing, which is actually we estimate the disturbances, which is due to the pitch, buoyancy forces and roll that we are actually trying to address, and then we are trying to compensate. So with that, the control scheme we have actually like executed the same control scheme which we have seen in the last slide. The same control scheme, only thing is they have used a disturbance observer for compensating those unexpected, you can say, effect. So now the vehicle is actually like followed certain pattern. The same way what we did, like initially start, it will go and pick and it will drop and come back. The same task we have given, we have compared with the earlier scheme which we were actually like discussed in the morning, right? Indirect adaptive control, and the proposed control we have compared. You can see the error wise it is actually like almost more or less equal. But if you come to the power, so the power consumption for total power consumption for indirect adaptive and the proposed control is almost like half. So which was actually like we felt it is challenging. So then we thought, okay, this is very simple tracking. So why can't we use something like a drilling task which need to be take place in underwater structure? So we have taken the drilling task also. So there also we could see that the power consumption is actually less. So that's what we have seen. And the third task we try to do it as a station keeping task. There also we could see the same trend was following. Somehow I did not put in this. But if you refer my paper, those details will be there. Along with the real-time experimentation will be there. So this is what one of the key achievement in the, like you can say, proposed control. So later on what we thought, okay, so this is actually simple PD. Why can't we use PID or probably like sliding mode? So if we see sliding mode, what is the problem we end up? So I'll tell you what is actually sliding mode having a problem. So conventional sliding mode will be like this. So you have x1 and x2. If you want to make a sliding region, so obviously like you are trying to make s equal to 0, that is what this region. And we will take a classical one which is actually like x2 plus lambda x2. So this is the straight line. If the straight line is 0, then obviously this is a sliding region. Okay. So what we are actually trying to do this is we call as a focus. So anything which is actually hitting on this will slide and will reach the equilibrium. So here I will take the equilibrium is actually like as 0, 0. So that way only I draw. So whatever it is actually coming and hitting, it will actually like try to reach the stable. So you just start anywhere here. You need to make a, you can just switching region. Then you have to have a sliding region. Correct? So now, if you use a classical sliding mode, so what is the problem? You have something like controller k into sine of. So this sine of s is actually going to give plus or minus 1. So this k only will actually like make sure if I have here, so it will come. It may go here also, then it will come back. As per the theory, it will come and hit and it will follow. But in reality, it may not actually like stay there. It may come and it may go like to and fro. It will start chattering. Okay. This is what we are actually like end up with a problem. Probably it will not extend, but it will actually like start chattering here. So this is the problem. Okay. People what they said, okay, you can take something like saturation of S. That too like they will come up with a boundary. So they said within this boundary it will act as a PD. So outside it will act as a sliding mode. This is the conventional way to reduce the, probably you can say the chattering. But even you see that if I actually like increase the mode, so what will happen? If I reduce, then again problem. If I increase also, I will have a problem. What is the problem? If I increase the boundary layer, it will actually like become PD only. So PD is actually sluggish, which we have seen. If I actually reduce this boundary layer, it will again give the chattering. Probably like if I reduce, it may hit like this. So it will hit, it will try to converge, but you have to stay here. No, it may not stay because you have sensor, feedback, the resolution, and your processing time. Everything is depends. So theoretically, like if you do simulation, that too like your step size is probably like 1 millisecond or 10 millisecond. It may get. You just increase 100 millisecond or 200 millisecond, you can see that the response is actually like very poor with the same control gains. So that's what the idea here. So what we thought, okay, we'll try to merge sliding mode with the PID. So this is actually like we call very simple. We call it as conventional sliding mode. There are other sliding modes also there, like integral sliding mode, even second order sliding mode. All those things are there. So we have tried to use something like SPID. So we tried to use sliding mode with PID control. So what we can actually see, for example, you have KP. So if this is the case, I am actually like trying to change that in a different way. So I actually like call this is actually like SPID, which is actually sliding mode based on, you can say like PID. So now the same thing I have actually like modified in such a way that I brought. So I assume that KD is actually like 1 and remaining I have made it according to it. Okay. If I bring this kind of thing, what I can actually like get? So simple I can call K into SPID. It is simple PID only, right? Because this K is actually like multiplied based on it. But if I actually like make this something like this or so what I am actually like trying to do, I am actually trying to do, so PID value I am actually trying to make difference. So now this will actually like give some advantage, especially this will give advantage. So this advantage I am trying to capitalize as one of the controls. So this people used to call adaptive sliding. There are many ways of adaptive sliding mode control scheme. This is one of the adaptive sliding mode. If I use simple K into SPID, it is actually like simple PID plus I call something like K0 into integral of SPID. So this is the adaptive term which I am calling. So this integral of SPID into dt, this will give the adaptiveness. So it will try to converge fast, but it will not actually have any oscillation because PID will not have oscillation like chattering effect, not oscillation you can say. The chattering effect will not be there. So this is what we are actually like trying to use in this particular paper. Okay. So here what we have taken, we were working on mobile manipulator, especially for mining industry. So for a preliminary work, we have taken a warehouse automation. So where one arm will be fixed on mobile manipulator, or you can say mobile robot. The mobile robot will have 4 degrees of freedom, or you can say 3 degrees with 4 motors. And on top you have one base which will actually like move up and down, and this entire thing can rotate, and 2 others. So this total manipulator degrees is actually 4, and this has 3. So totally like 7 degrees. So out of this 7, we are trying to get only the position XYZ. So because I can connect any spherical wrist at the end, I can get the 3 more orientation, whatever way I want. Because controlling simple spherical wrist is actually very simple. For example, I want to maintain certain degree in all 3 orientation. I can have the spherical wrist, which I can control, because that is actually like even morning Professor Gosal told, right? After 3rd and 4th joint, actually the effect of inertia is much negligible. So I can connect. Only issue is, so from this point to this point, the influence is much higher. The spherical wrist maximum probably like 1 or 2 kg, which will not actually like create much problem for variation. So the same scheme, like we are trying to apply whatever we propose here. Only thing, we modified everything in terms of like task space. So this is the joint space model. The joint space model I have modified into a task space model. So where this A is actually like defined like this, B, mu is defined, data is defined. The entire model I made it with the simplest way. So now I am actually like trying to apply the control scheme, which is I wrote like this. So this, which is equivalent to SPAD. You can see this. Zeta is actually like defined here. Zeta is actually like error dot plus 2 lambda into error, then lambda squared into integral. So this will actually like provide some kind of advantage, and we can actually like see that response here. So I have taken a very complex profile for verifying, because we try to verify in simulation. So if we are doing simulation alone, so in order to prove others, you have to take a complex profile, you have to take all complex analysis. So for that we have taken a very complex profile where all motions are possible. For example, you take lateral motion, longitudinal motion, vertical up and down, then sliding, or you can say ramp motion downward, upward, and circular motion. Even in this actually you are picking some unknown load and you are dropping the unknown load. So you are taking all complex profile and try to see the performance. So this is the performance. So without that uncertainty estimator, it was actually like poor, but still the control law is actually good. So whether you have this uncertainty parameter or not, still the control is actually like satisfied. You can see that it is almost like the maximum error during the initial picking and dropping, it is going like 6 centimeter. For industrial mobile manipulator, 6 centimeter is not big. Okay. That we'll see why it is not big. Because while actually you are picking and dropping, so you can always like anticipate, because you don't know what is the payload. So here we have taken 5 kg payload. So even if you are actually like not, you are closed your eyes and you are actually given sudden bottle, your arm also will go down by unknowingly. But if you are knowing that you are picking a bottle, you will be actually like process yourself and you will pick it. So that's why actually these errors are there. Otherwise you can see that the error is almost very close to 0. In order to understand the robustness of the control, because the control gain we have taken random, right? So like the lambda, gamma value, Kc, K0 and all, we have taken random. In order to verify whether the sensitivity is there or not. So we try to use the sensitivity, we vary it 0 to like 26 or probably like here 30, here 0 to 50, then 0 to 6, 0 like 0.5 to 2. So we try to like vary all the value and try to see, yeah, there is a sensitivity in Kc, because the control gain is actually 0, means basically remaining only trying to cover. So automatically only you can say the feedback linearization will not help. That's why you can see that it is actually like going more than like 10 centimeter in the initial experiment. Okay. And if you are keep on increasing, you can see that up to 15 it is actually like okay. After that it is actually very narrow, but more control activity will be involved. Similarly, the observer gain is not so much different. That's what we have seen even without uncertainty and with it is not much different. But the gamma is having a problem. If you take gamma is 0.5 indirectly square root. If you take gamma is 2 indirectly the square. So those two values will not give any value which is very close to ours. So that's why these two values are actually, you can see it is having much oscillation. It is having oscillation initially and then it is going somewhat peak unsteady or it is a steady state. So after that if you see that 1 to 1.5 it is optimal. So similarly the gamma value also we change. If we keep on increasing the gamma, the error will be reduced. But how long you will actually like provide? Your actuator requirement will be high. So that's why we will be like choosing certain appropriate value. Similarly, we want to check the robustness. We are saying the controller is actually supposed to be robust. So here the robustness we checked in different aspects. Like we have checked the disturbance frequency. So initially we assume that the disturbance is actually slowly varying, but we try to vary the frequency. So it is actually like while we are actually varying the frequency, we can see that the controller is actually like not able to overcome. So it can actually like perform certain level of fast varying disturbance. For example, you have a system and you are continuously oscillating, the system cannot. That's what it is actually like showing here. And this is actually an unrealistic situation. And similarly, the payload we vary 0 to like maximum payload, which is 2.5 kg. And you can see that the variation is actually like going up. But it is actually like getting stable. Initially, it is picking the load, it is actually dropping. But after a certain time, you can see that it trying to converge more close to 0. So similarly, the velocity of the end effector, they are varying from 0 meter, not 0, it is probably like 0.2 meter per second to like 2 meter per second. They are varying, and you can see that still the performance is actually like much closer, and uncertainty is actually like not involving much further. This way we have actually like tried to understand the robustness also, and the controller is saying that it is robust. And one another thing actually like we want to compare. So we are saying that everything we are trying to control in task space for mobile manipulator or kinematically related. But why can't I can do some optimization, try to get the inverse kinematics through optimization. Probably like I can apply numerical method. So here actually you can see that there are 5 unknowns, correct? So 3 known. So you can actually like start estimating with the numerical method. You start with some approximate and you try to get converged. So there are many schemes. Even if you want, you can use search based also, like genetic algorithm, simulator analysis. You can use simple gradient descent. So we have used gradient descent and we try to match with the same profile. We have taken a task based trajectory is common. So here we have applied task based control. Here we have actually like back driven. We have used gradient descent. And then actually like we have actually tried to find the inverse kinematics. And we have used the same control, but this is in joint space, this is in task space. So you can see there is actually like difference. So you can see that this, it is actually giving inverse kinematics in such a way that the vehicle entire motion is actually there. But here you can see that the vehicle is actually not much involved. So you can see once again. You can see the difference between the vehicle motions. So obviously you can see that here the less inertia which is actually manipulated. The manipulator involved more. In this case even the vehicle manipulator both are actually involved. Because inverse kinematics one of the solutions is actually like that. So you have to try to find which is actually global minimum that you have to take and substitute. But if you are taking a initial guess which is actually like bound with the local minimum, then you end up with a local solution. That solution may not be optimal. But if you use task-based control, automatically it is adjusted. That's what we are actually like trying to find. So this way we will actually like try to use the same scheme. The same scheme we have tried for actuator failure. So I told like there are 8 thrusters, 4 thrusters, where 1 or 2 thrusters are failed, how it will work. For that we have taken some like few videos I have, just to show. I hope the videos will work here. This is actually like a very simple task. So where the starting and ending point is there, the vehicle is actually like trying to go. Probably like, I'll just show parallelly. Yeah, this is the actual trajectory. So this is actually starting point and ending point. There are 4 thrusters. So 2 lateral thrusters, 2 horizontal thrusters. You can see there are 2 pink and 2 green thrusters are there. So I try to reach the point which is actually like in task space. It is just a set point control. The same control we have applied for fault. So now there is one thruster failed. You can see that the green is actually blinking. So this thruster has failed. The same target, but earlier it was actually straight away it is following. Now you can see that still it is following and reaching the target. Even one thruster failed. Even the same scheme we apply for two thruster failure, still it is reaching. Similarly, the same scheme we have applied for in the presence of current. So this is without fault and in the presence of current. So it is actually like trying to reach this target based on this current. It is actually aligned in such a way that it is reaching. So now the same thing which is with the current with fault. So there is a fault and actually like okay this current is actually like this is inclined. Try to see the same way. And still it is actually like trying to follow it. Check the practical result. Yeah, this is actually like without fault, and that point whatever I have shown is actually with fault. So the current is actually like passing in this direction, so it is actually aligned accordingly, and it is actually like reaching. The other one with fault, still it is actually like trying to reach. You can see the profile, it was different. Okay? That is what how the fault is actually like adapted. So this is just for set point. So I just try to use something like for task space. So this is a simple task space where it is starting from some non-zero error point and it is supposed to follow this circular profile. So there is no current involved, no fault involved. So here actually like fault is involved. So it is actually like trying to follow this profile with the fault. So one thruster is actually failed, it is actually like trying to follow. So we'll see if current is there, how it will actually like work. This all stuff we verified in C trial itself, and somehow actually like it is Korean government involved. I could not show, but you can actually like find our like web link where the post lab you can find those videos. Okay, this is actually like without fault. This is another side. The fault is actually in the other side. How it is actually like what that's what it is trying to show. So that same picture but it is actually like so this is what one particular like area where we can actually like apply either for something like external disturbance compensation or probably fault detection or you can say fault tolerant control. This kind of thing it can be used. But if you see any industrial manipulator, there are some problems where you have to deploy something like task-based control. Very simple example I will show you. So there is actually like some industrial manipulator. So this is supposed to be 90 degrees, this is supposed to be 90 degrees, and this is supposed to be parallel. So just imagine there is actually like some actuator like this. So this point need to be followed based on this up and down it may go. Now imagine this is actually like faultily designed. So this is also faultily designed. So how your task-based control will overcome or how the joint-based control will adapt. So this particular error, the joint space will not overcome. Even people can say that okay, I can use kinematic calibration method. I will calibrate every instant. So I will actually like readjust. So probably this kind of error you can actually like calibrate. Just imagine there is a joint. This joint is actually revolute joint. This revolute joint is having a clearance. So the clearance is actually something like this. Okay? So this is what your pin and this much I just exaggerated. So this much clearance. Now your calibration model cannot predict where this pinpoint is actually touching. So this is actually maximum delta error. So based on that only the calibration model will give. But in reality, it may not enter all the time this maximum delta. It may be like this much, or it may be even 0. It may be even 0. So that time actually like how you will actually like overcome. There we propose one control. This is actually like not a new one. So we used to like do dual loop. So what is dual loop? So it is actually like we call dual loop. So where the internal is actually like your robot. So robot will give velocity. The position will be taken from the sensor directly task based. So this will be taken and this is the desired. So you have a kinematic control, and based on the kinematic control you will actually like make a virtual velocity, desired velocity, virtual desired velocity. That you will actually like compare with your velocity and you will apply the torque or force. So this is actually like we call dynamic control. This is we call kinematic control. Simply people used to call this inner loop. This is like outer loop. So this kind of dual loop scheme will work, which will actually like minimize the error. Even it is actually like friction or kinematic error or clearance error or backlash error, which will be overcome by easy. Even if you are actually using the same system probably like 10 years, still this particular control scheme will work the same way all 10 years. But if you are working with the joint space or only task space, if you are working only with the task space like what I did earlier, that had a problem because it depends on the Jacobi. And you have to like convert. So I call this the force required. This need to be compared and convert as the joint space motor torque or motor forces. So this conversion is required. But in this dual loop, this conversion is not required. Because you are deriving only virtual velocity vector. It is actually like not much trouble as compared to this conversion. So this way actually like we can end up with the dual loop, which will be very much beneficial to us. So you have any questions so far? Otherwise I will just talk what are the other research which we are working in our lab. Because the control techniques I felt for robotics, whatever motion related I was actually covered. So hereafter if you want to work only like there are two other directions are available. One is the compliance or force control, the other one is cognitive control. So these two areas actually one of my hosts is working. So if you are actually like really interested in compliance control or probably like cognitive control, you can talk to Professor Begara in IITI. He is in electrical engineering. So even tomorrow Professor Datta is coming. He is very close to Professor Datta and he is my collaborator also. We have joined project 3 projects. So he is in that side like compliance control and cognitive control. I will show you one of the example what he was actually like working. I will just show you one simple video. So you all might be knowing Amazon picking challenge, correct? So why that Amazon picking challenge has come? Anyone know? So we all know like DARPA has a robotic challenge every year, correct? Similarly, last 2 to 3 years, there are many challenges up. Like Google has a challenge, Amazon has their own challenge. So this Amazon picking challenge is one of the critical for the current need. Like we all know drones also they are involved, correct? But drones can be involved for delivery. You just imagine, for example, you are ordering, especially Christmas or probably Onam time, you may order through Amazon, Flipkart. So you expect that the vacation for only you. The people who are working, they may not have vacation. And you expect on the festival day it's supposed to deliver. This is what you expect, correct? But you just imagine how many people will be there in the warehouse. If you order, somebody has to go and find the particular model and he has to put it in a dispatch, somebody has to pack, and then they have to dispatch. Probably dispatch they may have sufficient people, but this warehouse is actually like a dump, especially Indian warehouse you cannot compare at all. It is very horrible to stay inside warehouse. Then you have to find and put it in a proper basket and properly pack and deliver to the guy. So this is one of the challenge they faced. So for that they had a Amazon picking challenge, where they will give different kind of object. It may be jelly kind of thing, it may be concrete kind of thing. You have to take 10 different objects out of the rack and you have to put it. So for that only one university was selected from India, that is from IIT Kanpur. So he is actually like working